right. Let's wait a moment and then we'll start with intro. All right. Hello, everyone. Welcome to our Quirkcast weekly news. This is your host, Tim.
And I'm Mikey.
And this is Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. A few logistical things before we begin. If you haven't already, do join our Discord channel so you can ask us questions there and we can get to them. And if you're watching this on YouTube, feel free to ask questions at any time and we'll get to those as well. So without further ado, Mikey, I was reading this article. Actually, Tim, I don't know if we should pull it up, but I'll say it and I'll let you decide whether or not to pull it up. But an article about about being able to transmit communication messages across interstellar distances. So I guess it talked about using quantum mechanics and whatnot, and just want to gauge where should we start about this, Mikey?
Yeah, actually, let me share the article so audience can see the headlines. And here it is. It says that this is from physical org. I guess from quite a few websites from Physical Review. It says that mathematical calculations show that quantum communication across interstellar space should be possible, and that's quite an intriguing title. So yeah, what are the thoughts?
It's kind of cool. So people have thought about this for a while. Like, how would you communicate with some kind of alien species? One of the biggest difficulties is obviously if you're really far away, it takes a really long time for signals to reach the person trying to communicate. So could you have something like, in Star Wars where people on other sides of the galaxy can actually communicate with each other? It's an interesting question. Yeah, I think it's a cute little paper actually, because in this paper, I guess these authors asked the question: if you wanted to use quantum communication to communicate long distances, how well would it work? And they show that it would actually work quite well, and that if an advanced being were to choose a method of communicating across the galaxy, this might be the method that they might choose.
I see. Mikey, could you delve a little bit into what are the issues with classical communication? Like me just wanting to send a message to my friend in, the next nearby galaxy.
Yeah, the issue with communication is always the same. It's always signal to noise, right? Like if I shine a flashlight at you in Morse code, if you're really close to me, you might be able to make it out, but you're in California, I'm in New Jersey. If I flash my light, it would be really hard to see that signal, right? Because there's so much space, there's so much noise that can come in and drown it out. So yeah, that is always the goal of communication. The goal of effective communication is, even classical communication is finding a way to detect the communication above all of this noise that from the environment.
Yeah.
So one, oh wait, Tim, one question I want to ask before we get to the next point is space is empty. So why is it hard? Why is it hard? Shouldn't it be very easy for me to transmit a signal from here to anywhere else?
You'd think so, but if you look up, right, there's a lot of stars. If you're in a place with very low light pollution, you can see billions of stars. But even if you get close to the city, all of a sudden you can't see anything. There's actually a lot of crap in interstellar space. A lot of dust, a lot of gravitational wells, a lot of stuff that can kind of distort your signal. And we also live on the edge of the Milky Way galaxy, so one whole half of the sky is just completely muddled by dust. Yeah, so it's not as easy as you might think to send a signal. It's literally like shining a flashlight to another planet, across the galaxy, and trying to have them be able to interpret that.
Fair. Tim, why don't you go ahead? Sorry, apologies for interrupting you.
Yeah. I was just gonna add that so there are quite a few levels of distances, right? Like we have successfully communicated across our own solar system, right? Like NASA has run these projects, send a spacecraft to different parts of the solar system, and even those are not so easy. And these spacecrafts can receive radio wave signals, and there's delay in communication, and there's could be a lot of noise, signal to noise. But in here we're talking about something larger. We're talking about communicating across our own galaxy. Now that's many, I think millions of light years away. And of course, space is even larger. You can talk about across, from one galaxy to the next, and that's even the next, even larger distances. But I think so far, it looks like when I was reading the paper, it dealt with distances within our own galaxy. So we're not talking about the grandest, size of the cosmos yet. We're just talking about, hey, can one end of the galaxy talk to another end of the galaxy roughly? So.
Gotcha. That makes a lot of sense. So I guess let's jump into like the crux of this paper. Like what is like the way in which you can potentially do this? What makes this different than like other methods?
Yeah.
For you, Tim.
Yeah, I think someone said my voice is low. Let me try to make it higher. Hopefully that's better for our audience. Yeah. So actually, this might be a little too loud. Okay. Yeah. So one way to do this, obviously, like Mikey said, is to just kind of flash your light on the most basic level and flash it on and off at different radio frequencies, and that's how we communicate through satellite and so on and so forth, right? So that's classical communication. But interestingly, light actually has a separate property called polarization, which you might be familiar with for example, when you look at when you look at a pond using sunglasses, you see that depending on how you tilt it, the amount of light that gets transmitted can be changed. That actually has to do with the quantum nature of light. There's actually more information that can be gleaned from light than just the brightness of it or the frequency. And one interesting question is, this extra information, can it also be transmitted reasonably in interstellar space? Is it even plausible? And I think that's the question that this recent paper is trying to answer.
So just to clarify, is this extra information relevant because you get to pack more into like, I guess you send less of a signal and you get more information out of it if you utilize the quantum nature of these things? Or what is the significance of having extra information?
It's really just like another way of encoding information. It's not necessarily better or worse. It's just one that you wouldn't know about if you didn't know about quantum mechanics. And it's like, I think essentially what these authors showed is that you can use this technique as kind of like a fiber optic cable across the galaxies, right? Like why is fiber optics so good? It's a very effective way to bounce a beam of light without losing any of it with this continuous internal reflection by the wire. And it's not obvious that kind of a thing would work until you try it. You do the calculation. And yeah, these people are essentially doing the calculation for, what would it look like to use this extra information to communicate? It turns out that it has to be a lot more effective than trying to do it the normal way. And it's not obvious. So it's not like this quantum communication is inherently better.
Yeah, and also to add, like if we were to imagine there's some alien, totally speculative, obviously, right? We have seen no hints of aliens, but imagine there's a super advanced civilization, alien species, that have mastered technology well beyond our capabilities. It's very likely that they will have something like a quantum computer, which can process a lot more information at a quicker rate. And from that angle, then it's very natural that the signal that they are considering should be quantum mechanical signal, because right now, in some sense, when we look at a beam of light, we're kind of not looking all the information available. We're just looking at the brightness, basically classical information. But a beam of light could pack way more information, including the correlation if you have multiple beams of light, and these correlation, this information, when assessed quantum mechanically, it blows up exponentially. So the same amount of light can pack a lot more information, and if we have quantum computers, we could potentially process those info and kind of see, what the aliens want to send to us. I think that's kind of the thought experiment there, like imagining, what aliens might be thinking if they were really advanced technologically.
Yeah, these kinds of questions are always make really great scientific papers, I think, because have you heard like the Dyson sphere? Like, it's this guy Freeman Dyson had this idea that, if you imagine this alien reaches the peak of technological advancement, they would build a dome around the sun to collect the energy as efficiently as possible. So maybe we should look for these things. Like, if you just imagine that you have some alien species and you just assume that they have the best, they do everything the best, then their method of communication across the galaxy might be this quantum communication method, and we haven't been looking for that. So it's kind of cool. Like, yeah, it kind of opens up a realm of inquiry that didn't exist before.
So one question I want to clarify is that, just to set the record straight, it's not that you're able to transmit faster than light. You're able to transmit this information over a greater distance without losing much of the signal. Is that correct?
Yeah, quantum communication is not really faster than regular communication, so to speak. People often like to insinuate that this is true, but it's just plainly not.
Right.
Yeah, but it's a alternate method of communication.
Yeah. Let me just add. I mean, it might be a little unintuitive to our listeners. Like, this quantum information is just normally not. We don't normally think of it as important information because our technology hasn't really utilized it. But the crux of the paper is basically addressing that. So light has these quantum mechanical property, and as light travels through interstellar space, there's gravity, there's dust. All these could interfere with the quantum mechanical properties of the light. And the question is, if you do these calculations, do these properties pick up a lot of noise? That's the question. And it turns out that surprisingly, it doesn't. So one of the leading factors is gravity, because Einstein's theory says that light gets bent by gravity. So even classically, if you flash a beam of light, let's say let's say through the when it gets close to the sun, the beam of light can get bent, right? So and the brightness might change a bit depending on the gravity. So the signal has changed, right? But these are classical properties. The question is, does the quantum mechanical nature of light, the quantum mechanical properties of the light, change? And it turns out that they did this calculation, and the answer is it doesn't. It's a very particular property of light. And other effects, like when light going through dust and the interstellar stuff, basically, in space, it also doesn't get affected by much. So basically what they're saying is that they're not saying that you can definitely send signals through interstellar space, but they're saying that it's not impossible, basically.
It's essentially a cancellation effect, right?
Yeah, I mean, it's a little technical. It has to do with the fact that the light doesn't have a lot of internal structure, and that it's also massless. So kind of the interference from gravity cancels out. It's like a mathematical. I don't want to use the word miracle, but it's like it's a nice fact that it's plausible.
Luckily, like they found out that fortuitously, space has noise canceling properties. This method of communication.
Are you saying that Bose should get in on this?
Wait, Bose?
Yeah, the
Oh yeah,
headphones,
yeah.
noise
I mean,
canceling.
yeah, basically.
I
It's these.
see.
There's like a lot of things like this, right? Where you get lucky, like with technology. Like it didn't have to be that um, there even existed a way to communicate across these distances with
Hmm.
high fidelity. Um, but you know, I hesitate to say God, but they kind of set it up so that it makes it very convenient. Like, oh, so nice that electromagnetic waves exist. It means that I can communicate across the world. Oh, it's like so nice that space has this property. Now there's a way to communicate across the galaxy with high fidelity.
So actually, does that mean that I guess like one question I have is before this result came out, there were all these like astrophysics studies of light from stars like away and how they get red shifted and blue shifted and whatnot. With this, like, I mean, this is a more specific result about actually sending signals, but if that were not true, like, would that affect cosmology or astrophysics results, like the light you're seeing from
Oh,
stars?
yeah. Let me just add. So the redshift effect does exist, but those
Mm-hmm.
are more like classical property. What they studied
Mm-hmm.
was specifically what we call the coherence effect. It's the quantum mechanical part. And that's the interesting thing. The frequency of the light could get shifted, and that reduces the fidelity, what they call. But the quantum mechanical part, the phase part, does not change. So that's the interesting bit.
Ah, so the classical results still hold, but the quantum mechanical is
Right.
unchanged.
Exactly.
I see.
Exactly.
I see. What one question I was, what does high fidelity mean? Like, I would assume if I send a signal, not all of 100% of it's going to reach the other side like intact. It might be like 99%, 95%, 90% of it. Was there anything in the paper that gave a figure around that?
Well, I don't remember the exact number, but they did do a fidelity calculation.
Yeah, I think
Yeah.
they found that it depended on the fidelity is basically a measurement on how similar your final signal is to the original signal,
Hmm.
right? And like you mentioned, gravity could actually cause a redshift or blue shift, well, mostly redshift anyway.
Hmm.
And okay, and they did that calculation and they found that I mean the calculation is technical, that for certain kinds of light, like going from optical to X-ray, optical meaning like visible light, light has different frequency. I think they found that is it X-ray is not very good. They'll have low fidelity, but something like the optical light wouldn't be as affected by gravity. So so it's not like a slam dunk. But if you're aliens, I think you would imagine they'll be smart enough to craft signals that are more immune to this effect. So
Yeah, sure.
Ah.
Like, I mean, this is something we deal with, like currently with electromagnetic communication. Certain types of uh, um, radar signals are reflected by the Earth's atmosphere. So if you're trying to communicate with space, you have to know that you have to use these frequencies and not those frequencies. It's like a protocol.
Hmm.
I'm sure. Yeah,
yeah,
the
basically.
aliens know that.
That's fair. That's fair. All right. A super speculative question. I'm going to take a little bit of a stretch here. So, when you communicate, you're sending information from one point to another point. Can you, and I've heard that all of us are made up of information, quantum information. So, can you potentially use this technology to teleport?
So so indeed, if you read the paper, that's one of the things that they mentioned right from the beginning. But I want to quantify that. When people say teleportation, they mean quantum teleportation, which is a teleportation of a quantum state. Um, I mean, it's a very technical definition. It's not like literally a particle gets, instantaneously moved from one place to another.
Wait, isn't it? Sorry.
Well, it's the quantum information. Like you cannot, for example, you cannot transport an electron, right? Like what you can, like Like you can transport like a particle of light, a photon, for example.
Mm-hmm.
So if you can send quantum information across interstellar space with high enough fidelity, you could potentially teleport photons from one alien station to another. And if this is a big if aliens have constructed a machine that can rebuild an alien from photons and vice versa, then you could convert an alien into photons, teleport them from one end to another. They still have to travel at the speed of light. You cannot go faster. And then maybe, I don't know, if there's a station on Earth that receives that signal and reconstruct the alien from the photon. Yeah. That's the using this protocol, there's a slim chance that it may actually work, basically.
No, but yeah, but the problem is that the converting yourself to photons, you would have to have so many redundant photons because it's not perfect fidelity.
Right.
So you'd have to have so many redundant copies of yourself in such perfect. It would be. Yeah. So I really think it's important to stress that these results are strictly about communication, even though it is the same phenomenon behind what people call quantum teleportation, and even though it's arguable whether or not it's really teleportation at all. The result of this paper I think strictly deals with communication.
Do you know if any error correcting techniques are applied to this, or is it just like you send a signal using this protocol and it's all good?
Yeah, well,
you could apply traditional error correcting techniques on top of this, and on top of that, you could apply quantum computational error correcting techniques. The classical ones apply to anything quantum, and so here you have everything at your disposal if you actually are able to set up the hardware to do it.
Yeah, let me just add that this is sort of kind of in the sci-fi realm, but not completely. I mean, the state of the art is a group in China was able to teleport in this manner a particle of light through, I think, like 1,000 kilometers from Earth to a satellite. So, but of course, they spent a lot of money, launched a satellite, set up an entire experiment, and were able to do this. So, but just one particle, right? So it's sort of like a proof of concept. So this has been achieved through 1,000 kilometers. But the question is, can you do this through like many light years, basically?
Well,
it's not really practical for us, but again, it's interesting because
aliens.
It's a hint for what we could look for beings that are more intelligent than us.
It seems like if it took many light years to send it, it would take many light years to verify that it was correct. Because you can't go back.
Wow. Well, so... I mean, we actually have, unless we have the alien machines on Earth, we have to be able to decode it. So that's another problem. So with an intelligently designed physics machine, designed by the brightest physicists on Earth, we might be able to say unambiguously that certain signals are definitely from intelligent beings. We can say that, hey, like, oh, this is super not these. For example, if we receive some of these quantum mechanical photons that are coherent, we can be like, hey, wow, this is discovery. But we won't be able to quite decode what that message was yet, right? I would imagine. So that part, I don't think we will know. You have to make a guess, because depending on how they encode information, right, to the quantum bits, is anyone's guess.
So am I hearing aliens are afoot? Is that what's going on?
It's a new way to look for them.
So how difficult would it be to build this?
Yeah, I think we're already looking for alien signals through through this conventional channel. And I think in the past, we have gotten signals like quasars that we thought were aliens, because they're beams of light that just beam at us at regular frequency, and we thought they were aliens. But it turns out to be some of the greatest discovery in astrophysics. We discover these quasar objects, right? But yeah, this opens a new way to potentially look for interesting patterns in these beams of light. And maybe when we find something, well, of course, the first thing is we have to make sure they're not just some new interesting object. But the alien thought, I think, I don't know. Probably we'll have to wait, right?
Yeah, but luckily it's much easier to just hear something. It's much easier to listen than it is to talk.
Right.
So yeah, even though we're nowhere close from being able to establish such a communication system, to even feel the vibrations of it be a huge achievement.
Fair. I guess so. We're running up against time, and so I want to just use these last few minutes to give some concluding thoughts. So where do you think this leaves us, and like, what do you think the future of this research would be? Mike, you go first. I see you smiling.
There's like I don't know. It's like with all things like this, there's like a 1% chance that it could be the thing that enables something crazy, but in all likelihood, just a good shot at the crown.
Yeah.
What about you, Tim?
I would say that it's a very cute paper. I would encourage anyone to take a look at some of the popular science articles. Hopefully, don't get too hyped up about the alien aspect, but it's a cute result, and I think the impact on the field would be that it will encourage physicists to kind of think a little beyond just kind of the conventional things that we're seeing in astrophysics, and maybe this will lead to a new way to think about signals from outer space, and just new ways of thinking about these problems. I think that's probably the most impact that it will have, I think.
Fair. Mikey, what would you say to read this paper or not? Yay or nay?
Yeah, no, I mean you wouldn't know it just from looking at it, because there's so many what's the word, like what's the word, sensationalist sounding articles, but this is this is a good one.
All right, so I'm hearing yay from both of you, but don't get too excited about the aliens.
Yeah.
Is what I'm hearing. All right, on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, thank you for joining. Bye.
Yep.